Hi, everybody. Cool. Well, welcome to my talk. It's called Black Magic and Secrets, How Certificates Influence You. I'm Robert Lucero. My mentor is Andrew Case, who helped me get through all the fun parts of putting together a presentation and presenting publicly. So, I chose this title for my talk because certificates are kind of confusing if you don't really work with them all the time, and basically they're everywhere. So anytime that you're using a web browser to connect to a secure SSL HTTPS website, you're using a server certificate. You might not even realize that you're using server certificates behind the scenes when you're authenticating to third parties, and it's just a critical part of our security infrastructure. So, a little bit about me. I'm a physics major turned software developer. I've been working in software development for the last 8 years, and my first feature was actually working on IS Management's UI's server certificate feature, which is a way to make certificate requests, generate self-signed certificates, import signed certificates, set up bindings, and then in turn creating client authentication certificates and setting up client certificate authentication. So I had an opportunity to learn a lot about them. I continue to work in the space of my current job. It's a really interesting, challenging space. It's a critical part of what we use on the internet today. So what I want to kind of go over and what I hope that you guys will take away from the talk are two things. Number one is if you've never ever used certificates before, hopefully you come away with kind of how they work or the ideas behind them. And if you use certs on a regular basis, maybe you'll learn a couple ways to test, exploit, and maybe identify some best practices with the certificates that you use or the systems that use certificates that you work with on a daily basis. So let's jump right into it. A public key certificate is basically an asymmetric cryptographic public key with a verification signature. And the idea is that I can encrypt stuff with a public key, and in addition to that public key is a signature that you can verify to determine if you trust me, or if I'm saying if I'm trustworthy to encrypt with. And the example is this, is if I wanted to share secrets with everyone in the room, I could give everyone locks that only I can open, and you share back boxes and locks that only we can open. That's the cryptography part. But the challenging part is the signature part, the verification part. How do you know who I am? So if in real life, in kind of this public setting, to determine my identity, to verify my identity, you can ask me for my license, you can ask me in person, you can ask my friends, you can look up online, and there's various ways that you can verify my identity. Now, with certificates, you have a built-in systematic way with operating systems and phone OSs to determine if a public certificate that you're using is valid. And the way that that works is it works through root certificate authorities, which are installed automatically on your OSs, on your phones, and they're globally trusted authorities. So things like VeriSign, Digicert, Microsoft, all have put certificates on your boxes for you to use. Cool. So why do they matter? They matter because basically if you're using web communication, this is the standard way to protect your web communication. If you're protecting a sign-in page, you're probably doing it over HTTPS. If you're logging into a bank, HTTPS. If you're communicating with a web API, sensitive data, it's probably over HTTPS. And the other interesting thing about it is that they're implicitly trusted because you get the root CAs on your box automatically. You have to go out of your way to remove those root authorities. And if you do that, you can't use a lot of things. But the idea is that they're everywhere, you use them everywhere, and that's a way that you've implicitly trusted a system. So let's look at a couple of examples on how they work, the ideas behind them. Here we have client-to-server communication. It's basically HTTPS and SSL. And the things that use them are web servers and web browsers. That's an example. So you have Apache, Microsoft IIS, Nginx that have a server certificate, and on the opposite side, your client your client verification is in Chrome, i.e. Safari, your web browsers, and the clients are determining if they trust the endpoints, and that's kind of one example. Beyond that, people are using public certificates to encode data in JSON web tokens, so hiding certificate or signatures and claims. They're also used in API tokens, so you encrypt a bit of data that you use as an authorization header, and that's then used for communicating over a web API. Beyond that, beyond just the encrypting communication, it's also used for authentication. If you've ever used client certificate authentication, if you've ever requested one, if you use a badge that has your client cert built into it, that's one example. Another example is SAML. Behind the scenes, while you're communicating over SAML, you actually use a certificate. And it's also in other things like SSH authentication. You can actually put a public key that's then automatically trusted by the host that you're trying to connect to. And another kind of limited use example that I've seen at the couple companies that I've worked at is that they encrypt data using a certificate and then store it on the local file server, or they store it in a database that they can then decrypt and use. But it's the same idea, same technology, and they're validating the trust. So, what makes certificates vulnerable? I mean, there are a ton of ways that you can bypass this tool that people use. You can forge identities of certificate, you can forge CAs, you can bypass the certificate systems altogether. You'll find out that if you're using test certificates in your development environments, that's another way to get a hold and get past the public or the production level deployments of certificates. If I can inject my own certificate authority into your trusted store, you now trust everything that I issue. And the other part of it, less of the trust, more of the encryption portion of it, is you can force people to use weak encryption, or if I've set weak encryption for performance reasons, I'm basically putting myself at risk for having my secrets decrypted. So let's take a look at exploiting all of this. So there's two sorts of things that can be exploited. One of them is the library, so the things that are on the operating system, things that are on your phone. The other thing is if you're doing custom implementations. So if you're using certificates on a device or on a phone application or on a rich desktop client application, those custom implementations put you at risk. The examples here are this library vulnerability. Microsoft basically had a bug where you could forge and spoof certificates if they were improperly issued. So again, forging your identity of a signature. And then in OpenSSL, there's a way to force people to use a weaker encryption. And at that point, you can then brute force your way through to the secrets. But if you're doing custom implementations, all of this is handled not by a large company or an organization. It's handled by the developers that you work with, or yourself if you're doing development. The custom implementations are, how do I handle certificates when I interact with them? And there's a few examples up here that I've seen and I've tested with, and I've actually found myself writing bad code in those examples. So let's take a look at some of the bad development practices. Now, my experience is I've seen developers do a lot of these things. I've seen developers explicitly write in code and debug blocks, bypassing signature checks. So I've also seen developers explicitly check in test certificates and have blocks of code that say, if I see a test certificate, just trust it implicitly. I've also seen developers leave HTTP active when they're protecting an endpoint with HTTPS. So they're bypassing the certificate system completely at that point. So the idea is that libraries can't protect you if you've implemented it wrong. Systems can't protect you if you've implemented certificates incorrectly. And what's at risk is everything that you're trying to protect. So if it's your communication with your client, if it's service to service within your organization, if it's even things like issuing client certificates, client authentication certificates, you've basically exposed yourself to these sorts of vulnerabilities. So what I'd like to do is I'd like to give you a basic overview of the demo that I'm going to show you. And the idea is this, is that you have a you have a client application, a rich client application. Now this can be anything. This can be a phone application. This can be another web application. It could be a service endpoint. And the idea is that that client application, everything that they do, their communication is dependent on endpoint trust. So in this example, there's no authentication. It's basically talking to an endpoint, and if it's trusted via SSL or HTTPS, it's going to talk to it, and everything's fine. And in this case, with this workflow, the client app is posting data to the evil web API. The evil web API grabs the data, stores it, and then relays the data back to the good web API. And the good API, the good web API does whatever it was supposed to do, throws back a response. The evil API can then do things with it, and then our evil man in the middle then forges a response back. So real basic man in the middle, except there's no authentication, and it's all based on basically SSL and HTTPS trust. So it's basically that. Before we jump into the demo, are there any questions kind of about this? No? Okay, cool. So let's jump right into it. So I need just one moment to kind of prep all this so that you guys can see it. Oops. Keep changes. Okay. So let's take a look at the browsers first off. So here we are. I'm going to be using a tool called Postman. Postman is basically a Chrome plugin that lets you make web requests, and you get to craft the requests. It's kind of like curl, but in the browser. So let's take a look at the two endpoints. So here we have the good endpoint. Can you guys all read this? Yes? Great. So here we have the good endpoint. If you look, you'll see that Chrome is connecting to the website, and it's trusting it. And here it says, identity verified. It's got a little green lock. Everything's cool. Chrome is basically trusting the server certificate that I've issued for my endpoint. And it gives some great information. Now, if we take a look at the evil web application, you'll notice Chrome doesn't like it so much. It's got this nice X. It's got HTTPS with a big slash in it. It's warning you. If you look on it, if you click on it, it basically says, hey, the identity of this website has not been verified. It does not match the URL. It is not trusted. What are you doing here? That's kind of bad. So the other thing is I'll open this up in IE real quick to kind of give you the other half of it. IE is going to love the good endpoint. You know, it's trusted. It's got a little lock. Everything's great. And then if we look at the evil endpoint, it gives a big warning. It says, click here to close this web page. That's the good option for clients and customers and the users of the browser. And the bad action is to continue, it's to go on. And if I continue, get this big red, what are you doing? I don't trust this endpoint. I don't know why you're here. Just recently, browsers started doing this. You probably have started to see this happen more and more. It wasn't up until about, I would say, 4 or 5 years ago did all the browsers start basically showing this error to you and start forcing you to make decisions if it didn't trust the certificate. So now let's take a quick look at the API. So the API, it's fairly simple. If you're not familiar with web APIs or you haven't done any development with it before, come catch me afterwards and we can talk more about it. But all I'm doing is I'm getting some information from my trusted endpoint. I have some sensitive data that's in there. I have an ID, I have a name, I have a credit card, which is my sensitive information. And here, you know, we can post some data to it. Robert Lucero, and then my credit card number, my sensitive information. And if I go back to get the data, I'll find out that it's stored, everything's good. I've sent sensitive data over the wire and it's relatively protected. So let's take a look at the rich client application. So what I've written here, and hopefully you guys can see this. Can everyone read this? Yeah? Cool. So this client application, this Windows client, this console application is representative of anything. It can be a desktop application, it can be a web application, it can be a phone application. But the idea is that I've written some bit of code that now talks to a web API and an SSL endpoint. So let's just start it up. So by default, we're gonna connect. We're gonna send some sweet data over the wires. So Sally eSides, give it an ID, give some sensitive information like a credit card number. It's debugging, sent it. Now let's go back and let's go take a look at the endpoint. Let's go do a get on that web application. You'll see, Sally B sides got added. It's kind of down towards the bottom there. So what happens when I force my clients to start connecting to other endpoints? What is one way that they can protect themselves? So there's lots of ways that we can force clients to do bad things. Things like phishing attacks, things like malware misconfiguring, configuration for where it's going to talk to, forced relaying, forced redirecting. There's a whole bunch of examples where I can get a client application to talk to something else. And in this example, in this demo, all we're going to do is we're going to force it to talk to evil base URL. So now it's talking to the evil endpoints. Now we're going through the workflow that we showed in the diagram, which is I have a client that's now talking to an evil endpoint that's not trusted. So we verified that it wasn't trusted in the browser, right? You saw the big red bar. So here we're going to say Johnny compromised. It's now trying to send his credit card information. All right, let's see it. Let's go. Hey, it worked. Why did it work? When we went through the browser, right, we saw a big warning. Basically, the browser is telling us, why are you doing this? And it's giving the user an option to choose. It's giving the user an opportunity to say, yes, I trust it anyway, or no, I don't, because you've obviously failed some sort of check. Inside of the rich client, I didn't get that option. And if we go back and we look and see what happened, we see the man in the middle sort of work. So if we go to the evil API, he's now got Johnny compromised data. If we go to the trusted API, because we just forwarded the request, Johnny compromised shows up here, down at the bottom. It's a little hard to read. And then if you go to the evil API endpoint, we find out they're just posting credit cards. Because they were able to grab the secret, they ripped it open, and they sent it along because they were able to relay it. So let's take a quick look at the code. Let's figure out what was wrong. Why did that happen? And if anybody here is a developer, you're welcome to speak up and call out the line, the bug. We have this thing called configure HTTP client. We're doing some stuff here. What's gone wrong? What's the bug? Anybody? That's right. Here we are bypassing every server certificate check. What we've done is we basically listened to the libraries when they've connected over HTTPS, and we ignore what they say. It's basically what it comes down to. So what happens when we fix the bug? We can comment it out. Let's post some data. So Billy safe. He's posting his credit card information. Sure enough, we get an exception. There's a failure. The underlying connection was closed, could not establish trust relationship for the SSL TLS secure channel. And specifically, the remote certificate is invalid according to the validation procedure. So the libraries were trying to tell us to do the right thing. They were basically telling us, don't trust this endpoint. It's not valid. It's not signed. I don't trust it. We shouldn't trust it. But built into the code, I basically ignored that. I basically found a way to bypass the signature check entirely. Now, what ends up happening is you're developing in-house, or you're forced to use real certificates. Real certificates are expensive, right? You have to go to VeriSign and spend anywhere from $100 to thousands of dollars to get an SSL certificate. But if I'm deploying this to a test environment, I'm not using the same trusted certificates. I'm using a test certificate, or I'm using an SSL certificate, a self-signed certificate. And I may not be going through the same rigors of trusting that or making that a trusted environment. I might just be bypassing it in the code. So if you're ever auditing code, if you're ever doing code reviews, if you're ever doing testing an actual application that's connecting to a web endpoint, these are some things that you can try out. So now that we've fixed it, let's go try talking to, let's go say we're not compromised anymore. And then you'll notice Billy Safe fixed his problem. He's posting his credit card info again. We send it. It goes on. Rich client app doesn't notice anything. Seems like it's right. We go back to Postman. We're going to go get the data. And sure enough, Billy Safe, his stuff went right on through. It's trusted. Everything worked out great. All right. Cool. So any questions about the demo? Kind of the idea, simple man in the middle. So let's go back to the slides. Whoops. So here are some of the examples of bypassing certificate checks in sort of like client libraries. Here we have iOS. If you go to that page, it basically tells you, hey, here's how to bypass the certificate checks. Android, same thing, SSL socket library. .NET, this is their example. And if you want the links, they're going to be in the slides. They're just straight links. But the interesting thing, too, is if you ever go look at Stack Exchange or if you go at like Stack Overflow and you search for bypass or trust self-signed certificates or bypass certificate check, you'll see all sorts of examples where people have asked this question, and there's a snippet of code just like the one that we commented out where people are dropping them into their applications just so they can test, just so they can get around this issue. Kind of last thing I want to cover in regards to certificates is trust chains. So if you're ever in a position where you're having to manage multiple certificate authorities or you're issuing lots of certificates, intermediate authorities are really good ways at mitigating risk, and they're really good at kind of distributing the providing identity for your certificates. So the example is if I have a website, I'm going to issue certificates with my website CA, and if I'm doing client authentication, I'm going to issue certificates with my client CA. Fairly basic. When the validation happens, you'll notice that Service B certificate is signed by intermediate CA. Generally, your clients aren't going to know what intermediate CA is, but inside of intermediate CA's certificate, it will then say, hey, I was signed by this root CA. You can trust me, and the trust chain gets validated. That's the basic premise. They matter because, again, it's really easy to minimize service impact if one of your certificate authorities is compromised. So if all of a sudden my web server certificate authority was compromised, I don't have to reissue all of my certificates. I can revoke a single certificate, redeploy my CA, reissue the certificates without redeploying potentially thousands of certificates or hundreds of certificates. But the challenge is you're managing more secrets if you're doing like OpenSSL deployments of public or private keys. If you're doing it with Microsoft, it's another AD machine that you have to manage, which is a giant pain. But the biggest thing is if you're using a lot of certificates, this is a great way of mitigating the risk. So let's jump into the last part of it. The idea, the best development and test practices, test, and test with broken things. That's really what it comes down to. Test with an expired certificate, test with a self-signed certificate, test with an expired certificate. Basically find ways to test your systems if you're doing your own development to use broken certificates to identify issues. And the idea is If you know that you broke something in the certificate, but the system still works, something's wrong. The other thing is auditing endpoints. It goes back to that HTTPS and HTTP. And Yahoo, Twitter, and Facebook for a long time allowed you to log in via HTTPS or HTTP. Everyone who went over HTTP basically had their creds sniffed. If you went over HTTPS, you were relatively protected. If you know what SSL pinning is, so if you are doing like a mobile device development, you can pin a specific certificate signature, which is then trusted, and if that certificate changes behind the scenes, you'll fail the certificate check entirely. So I can issue a new trusted certificate for an endpoint, but because it wasn't the original one, I will still fail the check. And if you're using certificate revocation lists, basically ways to tell everybody don't trust these certs anymore, know how to use them, try them out, and make sure that you've developed the right pattern in there. And the last thing I want to talk about is if you are using test certificates, oftentimes they're checked into code, their hashes are checked into config, know that they're deployed, know that they're available, and if someone were to compromise your code, they could potentially steal your test certificates and use it against your real site. And that's it. So if you go to GitHub, you can get the demo code. I'll be posting the slides to GitHub. This is how you can get a hold of me. I'm representing myself. I'm Robert Lucero. I got Twitter. I got LinkedIn. I got all those cool things. And that's pretty much it. Are there any questions? Anything? Well, it depends. That's always the answer, right? So the libraries themselves are fairly well vetted. They're developed by like Apple. They are developed by Google and Microsoft, and they go through their own sort of security audits. But the default behavior is to fail everything that's not trusted. So if developers are to grab those APIs and start using them, they need to know what the other half of the system is, which is the certificates. So if I go buy a VeriSign cert and I use that against my API, everything's cool. But as soon as I go create like a self-signed certificate, then I'm having to start playing this game by installing that certificate to a trust store or bypassing the check or doing a debug case. Am I using a test certificate, yes or no? So that's kind of where the split happens. Does that answer your question? Most of them are, and it depends. The larger libraries, the more generally used libraries, are going to go through their internal audits. At least that was the case with Microsoft APIs, and I imagine it's the same thing for Android. Open source APIs are probably going to go through a similar practice, but more through community driven. So I wouldn't say that they're all secure by default because they all have vulnerabilities and they're always getting patched, but at least you're not doing the custom implementation, and you can manage that risk differently. You had a question. Or, yeah. Okay, so in my example, what I did was I basically changed the configuration. I basically said, don't use this website, use this other website, and from .NET's implementation, I could have an app.config that's not protected, and I could write something there with malware. Or it's a little contrived because there's just redirect the traffic quickly. But that would be the idea: is you get somebody to go to an endpoint that they don't intend to. No, not offhand. Generally, at least my experience is your operations team, because they're doing the deployments, and because especially if you're doing like an OpenSSL deployment, they're keeping very close tabs on the private keys, so they'll generally have an inventory of the certificates that they're using. Cool. Cool. So I have one last slide to kind of drop up here. I want to thank Andrew Case. He was my mentor. He took a lot of time out of his busy day job. You can get a hold of him on Twitter with ATTRC. And his book just came out, The Art of Memory Forensics. If you have a Black Hat badge, you can get a hold of him. He will be doing a book signing. But I really appreciate everything that you did. Thank you, Andrew. And that's it. Thank you guys very much for coming to my talk.